Hello everybody, my name is Fausto Carcassi and I'm going to be talking about how to implement the zeta distribution in PyMC3. So there's lots of already implemented distributions in PyMC3, but the zeta function isn't one of them. So I had to use it for some project, and so I thought, well, I have to implement it, so I'll make a video about it. So first of all, what is the zeta distribution? It's a distribution with a discrete support with the following probability mass function. So f of k equals, it's proportional to negative power, and then the normalization constant is the Riemann zeta function. Riemann zeta function, and obviously the Riemann zeta, okay, and it has support between 0 and infinity, and so the normalization constant is defined as the sum of k to the minus s between 0 and infinity, and that is the Riemann zeta function. So sorry, between 1 and infinity. So it's 1 divided by I to the minus s, and this infinite sum converges for s greater than 1. Okay, so what's the problem here in the implementation? The problem is that we need to implementing k to the minus s obviously is very easy in PyMC3, i.e. in theano. Implementing the zeta function is a bit harder because it has this infinite sum, which we can't do directly in theano. And so instead of using this expression, we use a different an approximation to the zeta function, which is defined in the following way. 1 minus 2 to the 1 minus s, okay, and then there's another sum, also infinite, but we can fix infinity here to a finite value, and it converges fairly quickly. Plus 1, and then sum from k equals 0 to n of minus 1 to the k, and then the binomial coefficient nk, and then k plus 1 to the minus s. Okay. So because this is a nested sum, so really we can bring this inside. So we can just move this here, move this back here, and this here. Okay, so what does this mean conceptually? Let's say that instead of going to infinity, we just do it up to 40 here, for instance. or let's say up to 100. What does this mean conceptually? Well, it means that a nested sum means that imagine a table here, and on one axis of the table we have the n's, and the other axis we have the k's, right? So let's say we start with 0 because it starts with 0 here, and then it goes, let's say, up to 100 here and up to 100 here. Now the sum here means that for each value of the n we consider all the values of k up to the value of n, and otherwise, because we are summing, in the table just has 0. So for instance, n here is 0, so we consider this, then n here is 1, and so we don't consider 0 anymore, right? But here, for instance, n is 0 and k is 1. Oh yeah, sorry, it's the other way around. So here k is 0, n is 1, so k is smaller than 0, is smaller than n, and so we do consider k 0 and 1. Then k 0 and 2 we also consider, and so on, in this direction. This is all good, but here, sorry, where n is 0 and k is 1, we don't consider, right? Because well, because k is greater than n. So you can imagine, and when they are the same, we do consider it. So this is also good. Okay, so you can imagine here a line, and yeah, wherever k is greater than n, then we don't calculate the value of this expression in the table. Okay, so how do we calculate the values in the table where we need to calculate them? Well, we just need to, well, there's 4 paths that we need to sum, and so I'm just gonna copy them here, and then we can consider them one by one. Okay, so the first part, this part, let's say, well, we are interested really in calculating the logarithm of the zeta function, because then we can calculate all the way up here. We can do the minus s log of k. So we calculate the log of the PMF instead of the PMF directly, because then we get more numerically stable results. Okay, and then here we calculate the log of this, which is the log of this, which is the log of this whole expression. And so, since this is a sum, eventually we can do log sum x, but for now let's just focus on calculating the logarithm of each one of these components. So logarithm of this is log of 1, which is 0, So here we can just forget about this first part and just say minus log of 2 to the n plus 1, which is minus n plus 1 times log of 2. So we are working in natural logarithms, so log 2 is not 1. Okay, then the second part, oh yeah, sorry, this is the log of this. So the second part is without the logarithm is just an alternation with k that ranges whatever in whatever range we want. In this case, at most 0 to 100. It's just going to be alternation of 1 and minus 1. So it's going to be 1 whenever k is even or 0, and minus 1 whenever k is odd. Yeah. Okay, then we can think about that later, how to implement whether we want to implement the log of that. Then the log of this, we get it from a PyMC3. It's already implemented, so we don't need to worry about that. And then the log of this is gonna be minus s log of k plus 1. Okay. Okay, good. So these are the bits we need to work on, and then we get the normalization constant, which was the only difficult bit about implementing the zeta function. Okay, so how do we calculate these individual bits? We can do that in Jupyter because it's fairly easy to see what's going on. So first, let's start by adding some useful functions here. So let's just add some the zeta function is implemented in SciPy, which we cannot use directly because we need something that works with theano to use in PyMC3. Then import theano, tensor st for various operations with the tensors, and then from PyMC3 dot distributions dot discrete import binom ln. So that's the ln of the this, which we can use directly from PyMC3. Then we need to just because we're going to be experimenting with theano functions, and they don't like it when you also import PyMC3. You have to set this to ignore. Okay, then just numpy, and then just in case we need it, matplotlib. Okay, so just as a test, so we have something, we have a benchmark to evaluate our implementation against. We can take zeta of 2, and then later when we implement it in theano, we can check if that's correct. Okay, and then let's consider the bits that we had earlier. So the first one that we need is just this one. So we have the logarithm. So this logarithm is minus n plus 1 logarithm of 2. And let's say that, so we need a parameter s. Let's just set that to 2, and then we need our the value for the approximation we are taking here. And so we can set that, say, to 100. Let's call that t equals 100. Okay. So the first component here, n here really means everything up to t. So if we are doing this, we can imagine doing this in a table. We have now let's first do it in NumPy. We have everything from 1 to t plus 1, right? Because we have here n plus 1 instead of n. So from 1 to t plus 1, and then we have minus that times np.log of 2. Oh yeah, as np. Okay, so that makes sense, more or less what we expect. Okay, so let's call that array 1. Okay, then array 2 is this part, so minus 1 to the k, and for that we can, let's call that scaling actually, because really it's we are scaling the results. So let's do that. So where np.arrange up to t is divisible by 2, we have 1, otherwise minus 1. Okay, then array 3, which is the binomial part. We can just take from from binom ln, which is the function we got from PyMC3, and we do it with, again, arrange from 0 to t, reshape minus 1, 1, from 0 to t. Okay, and this is going to give us a table of, well, let's have a look. Oh yeah, and we can evaluate that to get the actual value just for the NumPy experimentation. And note that this is minus infinity, exactly where we want, right? So if you remember this table that I drew here, it has x, which here means really 0, because then we want it to be 0 so that we don't sum it. So the log of that is minus infinity, and that's what we get in this table, in the corresponding points. So this table, this array, you can imagine it as being the corresponding to this table, and we get it's an array of in log space compared to this, and so we get minus infinity exactly where here we have 0. And therefore, we actually don't need to censor it later. We can just directly use this in the product, in log space, which corresponds, which is effectively a sum. Okay, and then array 4, remember, was this 4 component here, and so we can calculate it as minus s, which is the parameter of the zeta distribution t plus 1 plus 1. So yeah, you can see here what happens. Now, note that some of these are not actually tables, but we can exploit broadcasting to make them, to kind of broadcast them into the right shape. So the ones that go from, that kind of correspond to the ends, we can, so and remember that n is the first dimension in this table, and k, so n is dimension 0 and k is dimension 1. So the ones that correspond to the ends here, in the way that we have kind of coded them here, should be left as row vectors, and the ones that correspond to n should be transposed. They should become column vectors. And the only one that corresponds to the ends is array 1. So this array. And you can see here that that's the only place where n appears in n plus 1. Okay, so now we can, now that we have the 4 arrays, we can sum them, and the result should hopefully be the same as zeta. Well, yeah, there's also a little additional thing here, this that we need to also deal with, but otherwise we should just sum all over the table and it should work. So let's try it. So oh yeah, so first of all, let's calculate the log product of array 1, array 3 and array 4. Log product equals, so array 1 dot reshape, right, because of what I just was talking about, and then plus array 3 plus array 4. Okay, and then we can think about the scaling in a moment, and then we can calculate the output as well. We take the exponent. We exponentiate the log product. So we move that into normal non-log space, and then we multiply that by the scaling, and then we take the log of that. Now this is actually turns out to give more accurate results than using log sum exp. For some reason, I'm not exactly sure why. But yeah, I also checked with log sum exp, and this gives better results. And then we just subtract the log of this value, which is what was left here to do. So this part. Okay, so let's see. Oh yeah, and then we should also evaluate it, so it gives us an actual result. Okay, that's not working. Why is it not working? This doesn't lose. Oh right, I need to sum it, otherwise. Oh yeah, here I need to sum it, of course. Yeah. Oh yeah, I also need to evaluate the binomial here. Okay, good. And then it's just directly in NumPy. Okay, so right, that didn't work. Why did it not work? It actually did work, but I forgot it was in log space. So if you do np.exp, we get the actual right result. Okay, good. And it looks really accurate. It's accurate up to the, I don't know, to 15 decimal digits, I think. Let's see. Yeah, it's really close. Okay, good. So now we have it in NumPy, but how do we get it to work in theano? And really, like, it's quite similar. So yeah, that's one good thing about theano. You can really often just substitute NP with T, with capital T, and you'll get good results. But here specifically, we only need to calculate the gradient for S, which is the parameter. So this we can leave as it is. We can just calculate it with NumPy, and it's fine. The scaling as well. Then array 3, well, it's already in theano, so we just don't evaluate it. And then here as well, we don't need to really worried about it. So so it's already basically done. Log product. Yeah, so this is a fine. This is fine for theano already. And then the last line, which defines our output, is not too dissimilar either. So yeah, we just substitute mostly NP for T, and then we can just use NumPy to calculate 1 minus 2 to the 1 minus S. Right, so now output is a theano variable, and yeah, just to confirm that it does work, but you know, as it should, because we didn't really change anything. Yeah, of course, you know, I redefine, but zeta 2, it is the same. Okay, good. Okay, now we can just wrap this into a function, just for convenience. So let's call it Riemann log zeta. So it outputs the log of the Riemann distribution, and let's say we also give it T as a parameter and set it to 100, just because it looked precise enough, I think, for our purposes here. Okay, and then in order to kind of use this for in a PyMC3 model, we just need to wrap it in a density list. So let's do it. Well, okay, no, first we need to define a function which turns this normalization constant that we now have as a theano function into something that's into an actual density for the zeta mass function for the zeta distribution. So yeah, so we define a function which you call with passing a parameter s and returns the mass. And yeah, we can just use the definition for the zeta distribution that we saw earlier, and it gives us this expression. So just as a reminder for what's going on here, what we have calculated is this. So this is all the work until now. And then just now I wrote this expression, which gives us the log probability. Good. So now we have the zeta function, and then it gives us the log p for any value of zeta of s, and then we can just calculate a single zeta distribution with PyM density dist, which defines a distribution given a log p, and then we just pass it. Oh yeah, I didn't import PyMC3. Yeah. And then we can evaluate it at a specific point. So for instance, log p2.eval. Oh yeah, wait, I forgot to return here the actual function log p. Log p. Okay. Did I not call this? Because it's log zeta, right? Zeta. Oh yeah, didn't return output here. Okay. Okay, good. Finally. And then we can check if it's the same. Oh yeah, so we need to evaluate. Okay, so in order to check, because this is, so what this is this is the PMF of the zeta distribution with s parameters equals to 2 at value 2. So we can check if that's more or less correct by comparing it with what SciPy tells us the density is at that point, sorry, the mass is at that point. So from SciPy import stats, and then we can check, because stats has an implementation of the zeta distribution, although they call it zip, which isn't technically right, because the zip distribution is a censored version, is a bounded version of the zeta distribution, but they call it zip anyway. So so they call the parameter a instead of s, but it's close enough. So yeah, we have the log one here. Oh yeah, of course here there shouldn't be a log because it's already log space. So okay, now it's finally it corresponds. So so basically this is an implementation of the zeta distribution in PyMC3 done by calculating the normalization, writing a function to calculate the normalization constant, which is the Riemann's zeta distribution, or at least an approximation of it, which should be precise enough. And then based on that, we can easily calculate the actual probability mass function for the zeta distribution, and then we can use that log p to define a PyMC3 distribution with this utility pm.densityDist.dist.